Today's lesson is on something called improper integrals. Improper integrals are a definite integral that either has an infinite interval of integration or an unbounded integrand in the interval of integration, also known as a vertical asymptote. So if there's a vertical asymptote somewhere in the range, then it's an improper integral. So our tool that we're going to use is limits. Okay, so these are all examples of the first case where we have an infinite integral of integration. So this first one, the integral from a to infinity, we're going to rewrite as the limit as b goes to infinity of the integral from a to b of f of x. So typically, if we're replacing the top limit of integration, we replace it with a b. If you're replacing the bottom limit of integration, we use an a. So that's what we'll use here. This one can be rewritten as the limit as a goes to negative infinity of the integral from a to b of f of x dx. This one, we're going from negative infinity to infinity. So the first thing I'm going to do is split it up into the integral from negative infinity to some constant. 0 is kind of a logical choice. Okay, so I split it at 0, and then I'm going to go ahead and write the 2 with the limits. So this would be equivalent to the limit as a goes to negative infinity of the integral from a to 0 plus the limit as b goes to positive infinity of the integral from 0 to b. So let's look at what one of these looks like. So here's our first example. We have the integral from 1 to infinity of 1 over x squared. Okay, so how are we going to integrate to infinity? We use limits. So we'll do the limit as b goes to infinity of the integral from 1 to b of 1 over x squared. So the limit's going to go along until we have something to plug it into. The antiderivative of 1 over x squared is negative 1 over x. And we're going to evaluate this from 1 to b. So this will be the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Okay, well, if I'm looking at the limit as b goes to infinity, this denominator grows bigger and bigger. So this goes to 0. So all we're left with is 1. So this integral is 1. So we consider this to be a convergent improper integral. Our next example, similar idea, but instead of an x squared, we just have x. We're replacing the top, so we'll replace it with a b. Okay. Then we will integrate. The limit just keeps on there. Integral of 1 over x is the natural log of x. So this is going to be the natural log of b minus the natural log of 1. Well, as b goes to infinity, natural log of b also goes to infinity. Natural log of 1 is 0, but since this goes to infinity, we consider this to be a divergent integral. Okay, if it doesn't have a value, it's divergent. If it does have a value, it's convergent. So we'll rewrite this with the limit. B goes to infinity of the integral from 1 to b. I'm going to rewrite 1 over x squared as x to the negative 1/2, just to make our lives a little easier. So this will be, we'll add 1 to this, so that'll be x to the 1/2, and then we'll multiply by the reciprocal. So this is going to be 2 times the square root of b minus the square root of 1. Well, again, as b goes to infinity, this is going to go to infinity. So this one is also divergent. And so a general rule that you don't have to memorize, but is useful to maybe know, if you look at all three of these, square root of x, x, and x squared, if it's 1, if the degree in the denominator is 1 or less, then it's going to be divergent. If it's bigger than 1, it'll end up being convergent. But we can always just do the math to support that. Our next example, the integral from negative infinity to 0 of e to the x. So this will be the limit as a goes to negative infinity of the integral from a to 0 of e to the x dx. So that's just going to be e to the x evaluated from a to 0. That's going to be e to the 0 minus e to the a. Okay, well, e to the 0 is just going to be 1. As a goes to negative infinity, that's going to be e to the x as x goes to negative infinity. Well, e to the x looks like this. So as we go to negative infinity, that's going to be 0. So this answer is just 1. Okay, so we're going from negative infinity to positive infinity of 1 over x squared plus 4. So first thing I'm going to do is split this up into two integrals from negative infinity to 0. And from 0 to infinity. Okay, then we'll apply our limits. So this will be the limit as a goes to negative infinity of the integral from a to 0 of dx over x squared plus 4 plus the limit as b goes to positive infinity of dx over x squared plus 4, that integral. Okay, then we will integrate. Okay, so this integral is a tangent inverse, specifically 1/2 tangent inverse of x over 2. We'll evaluate this one from a to 0. Same integral from 0 to b. Okay, so again, keep the limits until you actually evaluate. So this is going to be 1/2 tangent inverse of 0 minus 1/2 tangent inverse of a over 2. This one's going to be the limit as b goes to infinity of tangent inverse 1/2 tangent inverse of b over 2 minus 1/2 tangent inverse of 0. All right, so as a goes to negative infinity, we're going to look at each piece of this. Tangent inverse of 0 is 0. And in fact, let me draw a graph of tangent inverse. Okay. Tangent inverse is the inverse of tangent. tangent is undefined at pi over 2 and negative pi over 2, which means the inverse tangent looks something like this. So the three pieces of information, tangent inverse of 0 is going to be 0. As we go to infinity, it levels off at pi over 2. As we go to negative infinity, it goes to negative pi over 2. So that'll help us with our integral. So tangent inverse of 0 is 0. As we go to negative infinity, tangent inverse of negative infinity is going to be negative pi over 2. We're going to add that 2. As we go to infinity, tangent inverse goes to positive pi over 2. So it's going to be 1/2 times positive pi over 2. And then tangent inverse of 0 is 0. So this becomes a positive pi over 4 plus pi over 4, which would be 2 pi over 4, which is pi over 2. The second type of improper integral is if within the limit of integration, your function has a vertical asymptote. This one's going to have a vertical asymptote when x equals 1, because that's what's in the denominator here. So I'm going to rewrite this one as the limit as a goes to 1 from the positive side, since we're going from 1 to 2, of the integral from a to 2 of dx over 1 minus x. Okay, well, the integral of 1 over x is natural log. So this is going to be negative natural log of 1 minus x, evaluated from a to 2. So that's going to be negative natural log. If I plug in a 2, that's going to be negative 1. So that ends up being 1, since it's the absolute value. Minus negative natural log of 1 minus a. So as we go to 1, this goes to 0. Okay, so what is the natural log of 0? Again, looking at a graph, natural log looks something like this. So as natural log goes to 0, it's going to negative infinity. So this one is divergent. This one, between 0 and 2, and these ones can be tricky because you might not recognize them as an improper integral at first, but between 0 and 2, this is undefined at 1. So the first thing I'm going to do is split this up into the integral from 0 to 1 plus the integral from 1 to 2. Okay, so we'll apply our limits. So the limit, as I'm replacing the top, so b goes to 1 from the negative side, since we're going from 0 to 1. Okay, and then we're going to replace the 1 down here, but we're going from 1 to 2, so I want to approach 1 from the positive side. Okay, so this is the same as x to the negative 3. So we're going to add 1 to negative 3, which makes it negative 2, which means I need to multiply by a negative 1/2. We're going to evaluate that from 0 to b. Okay, and same thing there. So we're going to plug in b and 0. So this will be -1/2, and then I'm going to rewrite this as 1 over b minus 1 squared. And I'm actually going to stop here, because if I'm going to 1, there's still a vertical asymptote here. So this is still going to go to infinity, which means this one is divergent. If even one part of it is divergent, the whole thing is divergent. Okay, our next one here. This will be the same as the limit as b goes to infinity of the integral from 0 to b of x squared e to the negative x. Well, when we're integrating something with a product, we want to use integration by parts. So I'm going to let u, and remember log poets, so my u is going to be my polynomial, and we'll derive that. And then my dv is going to be e to the negative x, and we'll integrate that. So it'll be negative e to the negative x, positive e to the negative x, negative e to the negative x. Draw my diagonals. Integrate across the bottom, but that's just going to be 0. And then use my alternating signs. Okay, so we've really done the integral already. So this will be the limit as b goes to infinity of negative x squared e to the negative x minus 2x e to the negative x minus 2e to the negative x. We're going to evaluate that from 0 to b. So if I plug in b, we're going to have, and I'm going to put the e in the denominator. So this is going to be negative b squared over e to the b minus 2b over e to the b minus 2 over e to the b minus, if I plug in 0, this is going to go to 0, this is going to go to 0, this is going to be minus 2e to the 0. All right, so as b goes to infinity, we have an exponential function on the bottom and a polynomial function on the top. So the denominator is going to grow faster on all of these. You could apply L'Hopital's rule, because technically this is going to be infinity over infinity, which is one of our cases we can use L'Hopital. But if you've got a polynomial, the relative growth, polynomial is just going to grow slower. So those will all go to 0. So you're just left with negative 2e to the 0, except for actually we were subtracting that, so that should be plus. So this is going to go to 2. All right, one final example, and this would be something you might see on a part of a free response or maybe a multiple choice question. So it says if the integral from 2 to x of f of t is this, then find the value of 2 to infinity. Well, I can rewrite that with my limits. Okay, well that's just going to be the limit as b goes to infinity. I'm going to take this and replace it here. Okay, and look at the limit as b goes to infinity of this thing. Well, looking at the degree on the top and the bottom is the same, because if we've got a degree 1 and the square root of a squared, that's going to cancel. So this limit is going to be the ratio of the leading coefficients, which is going to be 10 over the square root of 2, and then plus that 7. So that is our limit. So that's how we handle improper integrals.